So in the last few weeks we've been talking about z-scores, z-statistics, and this week we're going to switch and start talking about t-statistics. So with z-scores, we were using those to locate the proportion under the curve based on a single score. So for example, you take the GRE, so the graduate record examination, and you score a particular score. You want to know what percentage of people scored lower than you. To find that information, you would use what's called a z-score, just like we've been talking about. With a z-statistic, if you know your population parameters, you can compare mean scores versus the population. So that's a z-statistic, and so that changes things a little bit. Most of the time in research, we do not have population information. So again, a population would be every single person that you're interested in. We typically don't have the money, the time, the people. We just don't have the resources to go get that population data, so we have to deal with sample data. So that is why we're making the switch from z-scores, z-statistics, to what's called a t-score. So it's based on the same idea, so hopefully you've read your textbook chapter and you know that they are very similar. This formula in front of you should look very similar to what we've been doing because the t-distribution was derived from a z-distribution. So it's the same kind of idea here. So we have our normal distribution. We know that all of our scores fall under this normal distribution. The mean is in the center, plus 1 standard deviation, plus 2, minus 1, minus 2. It's the exact same idea. So with z-scores, we had a 0, a 1, a 2, -1, -2. It's the same idea with the t-statistic. So we can get our t-value, we can locate it on this curve, and then we can decide, okay, is this unlikely enough that we should count this as evidence for our alternative hypothesis, right? Can we reject the null hypothesis or not? And remember, that magical number is going to be p is less than 0.05. What that means, looking at this picture, is that it needs to be in one of the tails of this distribution. It needs to be very unlikely. So remember, a p-value is the probability of obtaining your data or your test statistic, your t-value, your z-value, those kinds of things, in a world where the null hypothesis is true. So you want that to be located out here in the ends. You want that to be a very unlikely event because you want to reject that null hypothesis. So we started with z-scores because we knew population parameters. Now we're moving into inferential statistics where we have a sample and we want to generalize to a population. So there are a couple of ways to do this. T-tests in general are going to ask, is this group, is this mean different from some other group? Sometimes it will be groups that you create in the lab. So you flip a coin and you get heads, they go through one protocol, tails, they go through another, and you want to test to see if they're different. Sometimes you will have a population parameter and you want to test your sample against that population parameter. That's what this is doing right here. So with a one sample t-test, you have a known population parameter. So this is basically what I was doing in that hypothesis testing video last week. We know the population IQ has a mean of 100, right? So if you tell me that your sample has a mean of 115, we know the standard deviation, right? So the population standard deviation, I believe, is 15. So we could work this out and compare our sample against the population. So that's what a one sample t-test is doing. Let me draw this out for you real quick. So I'll show you some calculations here in a second. But first I just want to make sure conceptually we know what's going on here, because that's really what I think is important. We'll work through a couple of these. I'm trying to kind of force you to understand what's going on. But really conceptually, that's what I want you to understand. I want you to understand what these tests are doing. So remember, we have this kind of setup where we have the frequency over here, right? We have our scores of x here, and then we can say, we have all of these IQ scores. We have a distribution of IQ scores, for example, from Aubrey, Texas, like I was talking about last week. So say, I don't remember what number I used, I would say like 100 is about there, 115, we have 100. So if this color represents our population, we know that our mean will be right about here. So I did that off a little bit, but pretend that this is just over a touch. So then we collect all of this data for Aubrey, Texas, and we find that their distribution looks a little bit like this, perhaps. So what this independent samples t-test is doing, it's taking this mean, so see this right here, this mean, and I think I cut off the image there a little bit, it is x bar. So it's taking this mean and it's going to subtract minus the population mean. So this is your numerator up here. So it's your sample mean minus your population mean. And then it's going to be over, what's this S again? So we know that's our standard deviation, our sample standard deviation, right? Over the square root of n, so over our number of participants. So what this is doing conceptually, this numerator is going to be the difference between groups. So let me get some space here to write that out. So this top right here, let me get my pencil back. Difference between. So in this case, in our one sample t-test example, our numerator, so again that's the top of our formula, is looking at the difference between our sample and the population. Our denominator here is looking at something a little bit different, so you also have to account for how variable these groups are, because you know everyone is different. And so what the denominator is doing is looking at this down here. Let me scroll down just a touch here. This is going to be the difference within groups, right? So even within Aubrey, Texas, so we give all of these students IQ tests, not everyone is going to score the same. Some people will score 100, some people will score 115, just the same as in our population. So we have some group variability and we have to account for that. So our t-test formula is going to be the difference between groups over, and I'll move this over, I think that cut off a little bit, so this should be the difference between over the difference within groups. So we have, in our one sample t-test formula, we're taking the sample mean minus the population mean, so that's the difference between groups, and then we're dividing by the difference within groups. So we have our standard deviation over the square root of our number of participants here. So that is within groups variability. So between groups over within groups, that is going to be the generic formula for these t-tests. So again, a one sample t-test, we have a sample mean and we're comparing it to a known population mean. Let's scroll down a little bit. Say, for example, instead of, say we don't have a population mean, instead we have two groups. So maybe, let's see, what could I do? I had some graduate students a few years ago that wanted to know the impact of stress on test-taking ability. So they had two different groups, and both groups completed the math portion of the GRE. So they gave them some GRE practice questions that were all math. In Group A, it was untimed. Group B was only allowed 5 minutes. So you get students, they come in to participate in your study, you flip a coin, and if they get heads, they are put into the untimed group, tails, they are put into the 5-minute group, and then you say, okay, complete these math questions. And you want to see how many they can complete, or how stressed they are, perhaps. So then you get a mean for your group 1, and you get a mean for your group 2, and you can do an independent samples t-test here. So this is the formula. It looks a little bit frightening in this formula. But let me just tell you again. So our numerator, so the top here, we're taking sample mean of group 1, so maybe the sample group of the untimed group, minus the sample mean of the timed group. So it's the difference between our groups again. In the denominator here, we're looking at sums of squares. So again, that's the variance within the group, right? So remember back a couple of weeks ago, we were talking about how far scores deviate from the mean. And sum of squares was one of the steps to get there. So again, this is looking at the differences within groups. Some people could go in, they have 5 minutes to complete a test, it doesn't stress them out at all. Another group could go in and you get 5 minutes and they just completely break down and have a panic attack. So there's always going to be within groups variability. Let me draw this out for you. So again, we're looking at, we have frequency here, and we'll draw our distributions. So say for example, I wanted to change that color. Maybe our group 1 is this green color, group 2 is this blue color, maybe it's a little purplish. And so we have some kind of stress scale from 0 to 100. So one group, I'm drawing a really horrible, let me redo this, that was really bad. Still adjusting to drawing and looking at a screen instead of my hand. So let's try that again. So this group maybe has a normal distribution somewhat in this shape, but you know, a little bit cleaner because I'm just bad at drawing today. Maybe the first group, their stress scores or something like this. So what our t-test is doing, again, in the top of our equation here, we're getting the mean from this group minus the mean from this group. We are looking at the difference between groups in that numerator. The denominator, on the other hand, let me try to get a different color here. So down here, we're looking at our within groups variance, right? So this purple group right here, their data stretches all of this way. So they're pretty variable bunch. Our green group here, this is their within groups variance. So this is the difference within groups. I'll just abbreviated difference. So again, in a t-test situation, we're typically looking at the difference between groups over the difference within. How you define the difference between is going to change. If you have two sample means, it's going to be the difference between those two sample means. If you're looking at a one sample t-test, you have that population parameter. You're going to be looking at the difference between your population parameter and your sample mean. In both cases, in both of these t-tests that we're talking about, we're going to look at the difference within groups in the denominator. That's going to be defined a little bit differently depending on which t-test you're doing. Here we're dealing with sum squares and controlling for sample size, those kinds of things. Up top we're doing the same kind of thing, but it's a little bit simpler because we're only dealing with one sample. So these are the two t-tests from this chapter. A one samples t-test, you're looking at a sample versus a population parameter. With an independent samples t-test, you're looking at the difference between two samples. So perhaps you assign two different groups, expose them to some kind of different treatment, and then you want to see if those two groups are different. Both of these t-tests are similar in that they are looking at, in the numerator, the difference between groups, and the denominator, the difference within groups. Okay, so let's take a moment well, first of all, this would be a good place to pause. So some of you have said these are too long. You can pause and come back. That's completely fine. Zaption should save your place for you. But let's switch and talk about some of these calculations, right? So here we have I'm in Excel now, so I can't draw, but this should look very familiar to you, particularly this part on the left here. So this is an example from your textbook. I forgot to write down what page, but you probably recognize it if you've read your textbook chapter. So they had 6 scores, a slow eater group, a fast eater group, So here what we're doing is just what we did a few weeks ago, right? So we have our raw scores, we sum those, we get the count there, the number of participants, we calculate our mean, and then we're looking at our deviations, and then the sum of squared deviations. So that's the sum of squares. You divide your sum of squares by n minus 1 to get your sample variance, and then you get the square root of that variance to get your sample standard deviation. If you don't remember this stuff, I'd encourage you to take a moment and go take a look at that, refresh that, make sure you understand what's going on here, because again, we're just building on top of these concepts. So we have two groups. The only difference is that I put one group over here on the left, our second group is over here on the right, and so I changed some of the labels here a little bit. So we have x1 for the slow eaters, so you have x1 minus x1 bar. It was just to differentiate the two groups, right? We have fast eaters, I designated it as x2. It's just a placeholder so that we know these two groups. And then I calculated sum of squares, variance, standard deviation, all of those good things. Now to extend that to a t-test situation, I just copied those relevant data points here. So again, we have our sum of squares for slow eaters, the sample variance, sample standard deviation, we have the n, and of course we have our mean. For now we're going to ignore the fast eaters here because again, a one sample t-test is looking at a sample versus a population value. So we're just going to use the slow eaters as our sample in this example, and then we're going to use the population parameter of 800. So here again, we have our one sample t-test formula. So it's going to be x bar minus mu. So sample mean minus population mean, again, difference between. And then we have our standard deviation over the square root of n. So again, that's going to be an assessment of our within groups variability. So to do this in Excel, it's pretty simple. So here what I've done, I can actually just do it again. So you're going to do equals, so we need our sample mean. So our sample mean up here is what, 600. We're going to subtract our population mean, so I'm going to click down here in that 800 box, hit enter, and move on to our denominator. So here we have our sample standard deviation over the square root of n. So I'm going to liberally use some parentheses here, so equals. I guess I could just do equals our standard deviation, so that's our standard deviation, click on that, divided by, here I'll do parentheses to get square root, sqrt, open parentheses, it's the square root of our n, so I'm going to click where our n is there, n is 6, close parentheses again, hit enter, our denominator there is 63.245, repeating. So our between groups difference is 200. Within groups variance, variability is going to be 63. So if we divide those out, we'll get our t statistic. So I just did equals numerator divided by denominator. Our t statistic is negative 3.162. So this is your t. So your t equals negative 3.16. The next step is to go into the t distribution table. So remember we had our unit normal table that gives us proportions under the curve for various z statistics. We also have a t table that does the same thing. You have to find your degrees of freedom. So degrees of freedom for a one sample t-test are going to be n minus 1. So our n is 6, subtract 1, degrees of freedom are 5. So if you look down in that table, degrees of freedom 5, for p equals 0.05, our cutoff value is going to be 2.571. So let me go draw this real quick. Let me find some space here. So we have our z obtained. We also have a z critical. So let's just copy those down real quick. Z obtained is negative 3.16. So z obtained negative 3.16. The z critical 2.571. So what we're doing here is we're looking at our normal distribution. Remember that. We know the area under the curve, all of those kinds of things. Actually, I did this wrong. T obtained, T critical, sorry. Again, these are very similar, and that's why I just made that mistake. They're derived off of very similar calculations, but again, with Z's you would have the population information. Here we're talking about t-tests, so we should be talking about t-distribution, so I apologize for that mistake. So what we're doing here, we have the same kind of things, right? So we have 0, we have 1, we have 2, we have -1, we have -2. So our T obtained is -3.16. So let me change that color. So we are way out here, right? For our result to be statistically significant, or in other words, less than 0.05, we would need to be beyond a T of 2.571. So that's going to be about right here. So it need to be here or beyond, or about here and beyond. Well, we know we are about right there, so we know that this is statistically significant. So at that point we can say our sample mean is in fact different from our population mean. To answer the question of how different it is, you'll need to calculate effect size, so Cohen's d, those kinds of things. I'm not going to walk through that right now. I'll talk about that in the SPSS video. There's a website. You can Google Cohen's d calc, and you can just enter in your values and calculate it really quickly. I'm fine with you guys doing that for effect size. So this is one sample t-test. So we're comparing a sample mean versus a population mean. In this case, we found our obtained statistic was beyond our critical value, so we did have a difference. We can reject our null hypothesis and say we've provided evidence for the alternative hypothesis. Now, similar thing with our independent samples t-test, but here we have two separate samples. So we have a sample of slow eaters here in the top. We have a sample of fast eaters here at the bottom. I've already calculated all of the mean, excuse me, the variance information for both of these, and we can input them into this formula for an independent samples t-test. Now, this might look a little bit different from what your textbook had. I tried to find one that would make the most sense, and in this case, sum of squares, we've done that, and so that was the easiest. So what we can do here again, we're looking at sample mean 1 minus sample mean 2 over sum of squares for group 1, sum of squares for group 2, n1, n2, minus 2 for degrees of freedom, and then times 1 over n, so on and so forth. So we're looking at the difference between over the difference within, and within this within groups calculation, sorry, I should have worded that a little bit better, we're controlling for sample size, because sometimes we can have one group with a lot of people, one group with not very many people, and that can create some problems for us. So here in the bottom, I've calculated this, so I can take T equals B4 minus B9, so I'm taking the mean of group 1 minus the mean of group 2. Here we're looking at, so again, liberal use of parentheses. We have the square root of, open parentheses, the sum of squares of group 1, so I just click up here, sum of squares of group 1 plus sum of squares of group 2, close parentheses. We're going to divide by the n of group 1, so you just click there, plus the n of group 2, you click here, minus 2. So we've done that right here, close parentheses. We're going to multiply that, and then open parentheses again, 1 over the n of group 1, which is 6, so you click there, close parentheses, plus 1 over the n of group 2, which is right here, which is also 6, and then you can close out all of those parentheses. Hit enter, and you get 82.664, or 398 if you wanted to be precise. So then what I've done here is take that numerator divided by the denominator. Our t statistic is negative 0.605. Now I'll upload this so that you guys can have it You really don't need to, some of these parentheses and stuff, I probably lost a few of you. Your eyes glazed over and you didn't want to deal with it anymore. But if you can calculate your sum of squares, your variance, sample standard deviation, you can just input that information here and this will take care of the rest for you. So if you want to do that in those few calculation problems that I've given you this week, please feel free. Of course, if it says complete it in SPSS, go ahead and do that for me. So we've calculated our t statistic. Our t statistic is negative 0.605. So let me jot that down for myself real quick. Negative 0.605 was our t statistic. So in this case, we need to know our critical value, right? So let me go back so that I can draw this. Get some fresh paper here. So we need to find our degrees of freedom for an independent samples t-test. And so to find degrees of freedom for an independent samples t-test, it's going to be the number of people in sample 1 minus 1, the number of people in sample 2 minus 1. So here we have 6 in both, so 6 minus 1 plus 6 minus 1, 5 plus 5. So our degrees of freedom are 10. So again, you go to that t table, the t distribution in the back of your book, and for p is less than 0.05 in the two tails and degrees of freedom of 10, our t critical was, I had this written down, 2.228. We know our t obtained is negative 0.605. So again, if we go back to our distribution here that we all know and love, and that I'm horrible at drawing for some reason, we have our distribution, we have 0, we have 1, we have 2, we have 1, negative 2. Let me change that color. So for this to be statistically significant, we'd have to be beyond our t critical value of 2.228. So it would need to be roughly here or over, roughly here or over our, let me get a different color here. Our t obtained, negative 0.605, is going to be roughly right here. Right, so that's where our t value is. In this case, we are not within the rejection region, right? So the rejection region would be this stuff out here, this stuff out here, and of course those should be equivalent. My drawing is just that bad today. It is not in this region, so we fail to reject. Right, so we fail to reject our null hypothesis. So H sub O, fail to reject. So that is an independent samples t-test. So again, we have two groups. Say one group has a high stress situation, the other has a low stress situation, and then you want to look at how well they perform on a math test. You want to look at their reported stress, whatever your dependent variable happens to be. You can compare those means. You're going to do the difference between groups over the difference within groups. That gives you a t statistic that you then compare to a t critical based on your degrees of freedom and see if it's in the rejection region. If it is, you can reject. If it is not, you fail to reject, which we did here in this example. Now again, to know how different these groups are, you need to calculate Cohen's D. So Cohen's D, you can Google Cohen's D calc. The first link that comes up is a really great calculator. You just input your sample means, you input your standard deviations, and it calculates Cohen's D for you. So to know how different these two groups are, you need to calculate Cohen's D, right? So P tells us, remember, P, is there a difference? Effect size, which Cohen's D is an effect size, will tell us how different, which is really what we would like to know. Now, in your homework, please calculate these using Excel. You can calculate them by hand if you would like. There'll be a separate section, actually. Your midterm is where you will use SPSS. So those videos will be next up. I'll show you how to do one sample, independent samples in SPSS. I'll also show you that Cohen's d calculator that I've been talking about. And as always, if you have any questions, this class is tough. I know it's tough. I think I mentioned the first time I took statistics as an undergrad, I got a D. I was just so bad at this stuff. I got caught up in all of the math, got completely lost, got a D, ended up having to repeat it for credit. I don't want you guys to have to pay for this class twice. If you have questions, please let me know in the comments here. I go through those every week, or send me an email. I can record more videos. We can do another session. We want you to understand this. We want you to pass it. So let me know your questions, and I'll do my best to help.